Record. Hello, I'm Zinedine Oz, doing master degree at University College Dublin. And today I will talk about our paper subMFL, computable submodel generation for federated learning in device heterogeneous environment. Contents will be background, related work, computable submodel generation in federated learning, simulation setting, result, and future works. This is typical smart city, and we see now other applications like air pollution or smart environment, smart building, electrical vehicle charging, and so on. And characteristic of this environment is distributed, dynamic, mobile, and each device are partially observe their environment. And since they keep data and collect data, there's a privacy and security concern, and also latency, and they are resource constrained, and their data can be heterogeneous, and device hardware power can be different from device to device. And in such environment, each device are not able to generate a good machine learning algorithm by themselves because their data can be very limited. And also, as I said, their hardware can be very limited. For this reason, distributed machine learning is proposed. In distributed machine learning, first, a cloud server requires data from devices. And these data sets are shared with a cloud. And cloud trains a global model, and this global model is shared with all of devices. This technique has a lot of advantages like improved performance because all of data are kept in one place, and increased accuracy since they are owner of the data now, and also they can train larger machine learning algorithms, and they can scale large input data sizes. But also there are some disadvantages like low latency and privacy and scalability because data need to be shared with somewhere else, and especially in terms of GDPR and other restrictions, this can cause some issues. For this reason, another technique is proposed called federated learning. Federated learning system is a bit different than distributed machine learning because training stage is only on device side, and the task of the server is just aggregating local models. It's like that. First, instead of requiring data from devices, cloud instead of requiring data, cloud sent a global model with all of devices to be trained. And then each device trained this global model on local with their local data, and then a local model is shared with a server, and that local models are aggregated like an average, and another global round starts, and that's the global model is shared again. By this way, each device own a global model like trained with all of data sets, but nobody knows any other data because there is no data communication between server and device. And advantages are data privacy because data stay local, and data availability. It's a collaborative learning technique, and also distributed and also decentralized. And it has scalability advantages and fault recovery and high availability. And also communication efficiency because instead of data communication, there's only model communication, and its size are lower. But there are some challenges with federated learning as well, like device heterogeneity, because we cannot expect that all of devices can train same global model. And also data heterogeneity. We share a server, we share same global model, but maybe their data is different. Like we cannot train same global model with video or text data, for example, or time series data. And also, maybe there is lower communication overhead, but still there is communication overhead because there are model transmission, and during this communication, if model can be smaller, this communication overhead challenge will be decreased. And in this paper, we focused on device heterogeneity. When each device has different computational power and also resource constraints, how can we tackle with this scenario? In standard federated learning, we can send a dense model, but when we send a dense model, model learning constraints are lower. However, participation can be lower. But when we share a more sparse global model with all of devices, okay, maybe participation is more because more device can train that sparse model. However, on the other hand, that model can have learning constraints. For this reason, there should be some technique to tackle with this scenario. And model comparison technique can address some of issues. For example, split learning, one of them, knowledge distillation, lower rank factorization, quantization, and pruning. In this paper, we worked with pruning because we want to continue to work with pruning more. Currently, we are targeting to tackle with device heterogeneity, but in the literature, that pruning compression technique is proposed for device heterogeneity, communication overhead, and data heterogeneity in federated learning. Since it has potential to tackle that three challenges, we pick the pruning. And let's look at the related work that tackle with communication overhead using pruning. In FET SCR, the target is to send only necessary parameters during communication using pruning on the server side. In Hermes, each device finds a small sub-network by applying structured pruning. Only the updates of the sub-networks are communicated between the server and the devices in order to improve both communication and inference efficiency. In AdaptCL, to run the overall federated learning process with all devices synchronously in a heterogeneous environment, the authors propose to send different stage pruned models to each device to converge the response time and each device update. And there are some other work that tackle with data heterogeneity. Like one of them is aiming to server-side cluster devices based on received parameters, and the server aggregates each cluster parameter separately. In another work, a local pruning mask is used with respect to both pruning-induced errors and the notion of minimum converge index. There are a bit more work in device heterogeneity. And for example, the first one is prunefl. First, an initial device is selected to prune the initial global model. Then the further pruning involves both the server and device during the federated learning process. Thus, a good starting point can be found for the FL process involving all devices. In another work, before the FL process, it is suggested to run local data-aware pruning in order to achieve device-led models. In another work, it is proposed that during federated learning training, the server determines a pruning ratio and allocates various resources adaptively. Then a threshold-based device selection strategy is used to further improve the learning performance. In FedPrune, it sent randomly different submodels to devices from the server side to find the optimum submodel. In FedMF, enables each device to avoid training to entire global model by determining specific pruning ratios. And in FGORT, system diversity is considered and the same model size is not distributed to all devices. Instead, the model size is tailored to device at hand. Okay, is it think studies that address device heterogeneity, there's a need for determining a specific pruning ratio, or the computation cost of pruning process is left to device side. Since already training occurs on the device and doing the pruning process also on device causes more energy consumption. And in our work, we proposed that using one global model, which is dense, it's possible to prepare a set of sparse model, and this sparse model can be shared with resource constrained devices in an order from more dense to sparse, and this can tackle in some of issues. And our contribution is the combination of server-side model pruning. The over-pruning process on the device side leads to energy loss. In our work, the pruning stage is completely carried to the server without the need for any data sample. And compatible submodel generations, by ensuring that the trained dense models weights are transferred to generate submodel, resource constrained devices benefit from the data used to train global model by beginning to train a model with satisfactory accuracy. So there is actually a kind of transfer learning effect here, because that dense global model is trained with some of the devices which are able to train it. And when we generate submodel, that submodel's weights are actually carried from that previously trained global model. And increased heterogeneous device participation rate, subMFL, tailors the Federated Learning paradigm for environment that include heterogeneous devices with various level of computation resources by assigning suitable pre-trained and compressed initial global model that fit their resource. Let's look a bit more how it works. First, servers share a dense global model with all of devices. And of course, not all of them can train it. But some of them are training this, and now we have a trained dense model. Then we prepare a set of sparse model with threshold-based way. And by this threshold, some of the weights in the dense model are decreased to 0. And we increase this threshold step by step. By this way, we have 9 different submodels, because we start to this threshold from 0.1 to 0.9. It's not increased more because the biggest weights already 1. So weights of global model in machine learning are between 0 and 1 that we used. And this threshold, that's why increase 1 by 1. And if you look at the pseudocode, server generates a global model architecture, and this global model is trained with all of devices. Then submodels are generated from that global model, and for each global model weight, we look at the devices. Maybe there are some of devices in the dense model, for example, at the beginning that they reached their target accuracy. Say, for this reason, they not join to next training of submodel. For this reason, some of devices are preferred to leave the system because if they train more, they will lose energy. Since they reach their target accuracy, they can leave, and then this submodel is trained with remaining resource constrained devices. In the training process, we used 100 global round. Server shares model with devices, and server receive global model from devices. And there's a model aggregation stage. We used Fed average algorithm, and to use submodels, we generated them by threshold-based, as I said. It starts with 0, but we increased with 0.1. So each weights in the model, that current global model, which is submodel, they're decreased to 0. By this way, sum of weights in the model are now 0, and it's more sparse, and it is less energy consumption required. It consumes less energy by the sparsification. For this reason, resource-constrained devices can train it. And for each device in D, if they reach their target accuracy, they just remove, the system is removing that. The actually device themselves are exiting from the system because they reach their accuracy. And we coded this simulation in PyTorch and Flower, and we used 1,000 devices and shared data randomly with an equal sample size. And 10% of devices able to train the dance model. So we generate a dance global model only with 10% of devices, because other cannot train it because of their resource power. And we used MNIST and Fashion MNIST with LeanNet, and we used ADAM with 0.001 learning rate as optimizer, and global round was 100, as I said, and local epoch is 3. When servers share model with devices, how many times they train it, it's 3, so local epoch is 3. And the validation data percentage is 10, and batch size is 64. Availability is 30% due to factors such as mobility, low energy, and connection issues, because we cannot expect that all of devices, even though they have enough power, maybe sometimes they cannot train or send their local model with the server, even though they have a good hardware power. And we used standard federated learning as baseline, and we compared accuracy loss and participation number, global sparsity of standard federated learning with subMFL. Okay, for example, let's look at the accuracy and global sparsity percentage. When we generate different sparse model at the server in standard federated learning, in all of cases, the accuracy of model is always between 10%, because there are 10 different output of the model, because it is always prepared with random weights. We don't know what to do. And all of devices start to train a model with random weights. And when the model is more sparse, for example, 0.8, participation is more for standard federated learning. However, at the beginning, the accuracy of the model is always around 10%. However, on the other hand, at the beginning, when we share a dense model with all of devices, and when 10% of them train them, we see that accuracy can be high. And when we generate submodel with this trained global model, we see that pruning can help us to generate a set of submodel. However, the submodels accuracy are still high. And even we can see that sometimes there can be a bit accuracy increase despite pruning model more. It's because of the over parameterization in deep learning, because some of weights actually can learn noises from data. So when we remove some of the weights which are not important, actually it even can increase model accuracy. Because normally we know that when we compress a machine learning algorithm, there are accuracy loss. And we see that accuracy loss for MNIST data after 0.8 is decreased to 6, but still it's a good starting point. So instead of picking one of the model in standard federated learning, starting with a dense and preparing submodels is reasonable, we see from results. And also this B chart shows that the number of participation of devices also still high, despite the this accuracy change of the submodels. So still we have good model, good submodels, but accuracy is also high. And result for fashion MNIST is also a bit similar. We see that despite pruning model with different threshold values, still accuracy can remain fine. And after a point, it can decrease. But it is expected because when threshold value is increased, more and more, some of the important weights can be lost. And also for participation, it is same. And we can see results for this table as well. First, at the beginning, global model accuracy for standard federated learning is always like around 10. Same for the subMFL as well. But when we share smaller model, still they're always around 10%. But since we trained this global model and then we generated that submodels, we see that accuracy is very good and we can share them. By this way, they can resource constrained devices can reach a better accuracy in a shorter global rounds. So they do not need to even train model more and more because their starting point is good. And participation also increases. It's same for standard federated learning because when we pick a smaller model, however, in subMFL, we see that accuracy is always good for the data set used. And advanced for the future works, advanced model complexity methods can be used. For instance, a combination of pruning with quantization can both address device heterogeneity and communication overhead, because in pruning, we decrease some of the weights to 0, but size of the model actually is still same. So if you quantize it, it can be even lower in terms of size. And combining submodels for generalization, since the sum of the submodels will be trained with only a subset of devices, those submodels wouldn't be general enough. For this reason, the average of the same parameters from different submodels can lead to generate more general models. And when we share this submodels in order, we have at the end of the system, we have one global model, and then we have 9 different submodels. At the end, if you combine that's all of the common weights, make an average, and combine those submodels, we can increase model generality, because not all of devices are training all of the global model, and to have a more general model, that those models can be combined. Thank you very much. If you have any questions, you can ask me, and please do not hesitate to reach me for future questions or a possible collaboration. I'll be very happy to hear from you. Thank you very much.